So here we are at chapter 16, which is about nuclear chemistry. Most of us know it as radiation. And for you old-timers or new-timers or whatever, I guess they remade it, this would be like things that turned the Incredible Hulk into himself. You know, Dr. Banner was messing with some gamma rays and fried himself, and all of a sudden you turn into the Incredible Hulk. Now, while that isn't true, radiation is what we call mutagens. They will go ahead and attack cells and distort them and possibly destroy them. Hence, radiation treatments for cancer. Okay, but you know, as we know, anybody that has gone through radiation therapy, it can be quite taxing. Also, CAT scans work off the idea of radiation. X-rays work off the idea or the theory of radiation. So this first chapter is basically we're going to describe these particles of radiation and their alpha, beta, positron, and gamma radiation. I always call gamma radiation the mutation radiation, if you will, or the superhero radiation, just because of the power behind gamma radiation. So, key math skills, using positive and negative numbers and calculations, we'll get to that. Solving equations, pretty straightforward for this. Interpreting a line graph, you know, y equals mx plus b. Slope, stuff that we should already have buried into our wonderful noggins and all that good stuff. So, conversion factors, counting protons and neutrons, writing atomic symbols for isotopes, and balancing chemical equations, which we should already know how to do. Okay, so radioactivity comes from an unstable nuclei. So what do we know about the nuclei? We know it's made up of protons and neutrons, right? With the exception of hydrogen, which is just a weird boy or girl that can exist without a neutron. Okay, so defined as a nuclei in which the nuclear forces cannot offset the repulsion between the protons, and we'll get to that, and that are radioactive, emitting small particles of energy called radiation to become more stable. So elements that are naturally unstable don't like being that way. They're like, oh no, I want a friend. You know, they want to be part of the cool kids. And so what they do is they shed off different materials in the form of radiation, and this is what makes them stable, all right? So a radioisotope has an unstable nucleus that emits radiation. Can be one or more isotopes of any element, okay? It includes the mass number and its name. So iodine-131 is radioactive. And it's used in the diagnosis and treatment of thyroid disorders, okay? So when it says iodine-131, that is its atomic mass. Its atomic number, then, is 53. So if we want to know how many neutrons are in this, we can simply subtract 131 from 53, and that will give us, 78, okay? And that's how we know how many neutrons are actually located in this atom. Okay, so we have things that are called stable isotopes, and an isotope, again, is it having varying numbers of neutrons in the nucleus, okay? And so magnesium, 24, is a stable isotope, okay? Iodine-127 is a stable isotope. Uranium, not a stable isotope, okay? Doesn't have any stable isotopes, meaning that it is radioactive from the word go, all right? So if we look at magnesium, we do have two other isotopes that are unstable, magnesium-23 and magnesium-27. So magnesium-24, we have a stable isotope, meaning that it's not radioactive. But then we have magnesium-23 and 27, which are iodine-125 and 131, both radioactive. Now uranium, and if you think of uranium and you hear these terms like enriched uranium, these are things that we use for atomic weapons, nuclear weapons, and things of that nature. So we've got these unstable isotopes, such as radioactive isotopes, uranium-235 and uranium-238. So radioisotope emits radiation such as things called alpha particles. They're identical to the helium nucleus. nucleus, okay? So the helium nucleus contains what? 2 protons and 2 neutrons, all right? Beta particles are high energy electrons, and we'll talk about how they get shifted out. Then we have what are called positrons, which are emitted from the nucleus, and then we have pure energy radiation called gamma rays. All right, so how do these things come about? Well, an alpha particle has a helium nucleus, 2 protons, 2 neutrons, has a mass number of 4, and a 2 plus charge. It's a low energy compared to other radiation particles. And we'll talk about what we mean by low energy in a second. We then have beta particles. It is a high energy electron, and it's being shot. It's like flying at you. It has a mass number of 0, as we know that electrons have an extremely low mass, and a charge of -1. Okay, it forms in an unstable nucleus when a neutron changes into a proton and an electron. Okay, a positron has a mass number of 0 and a charge of +1. It forms in an unstable nucleus when a proton changes into a neutron and a positron. All right, so proton in the nucleus right here. New neutron remains in the nucleus, and the positron goes out of the nucleus. And remember, nucleus center, and we got our electron clouds, which I know looks like a solar system. It's not really an accurate representation, but that positron goes flying out of the nucleus. Then we have gamma ray radiation. It's high energy radiation. It has a mass number of 0 and a 0 charge. Okay, it's a form of energy emitted from an unstable nucleus to give a more stable, lower energy nucleus. Gamma radiations form when these guys are trying to become stable. They're like, man, this is just not working out. So you get voted off the island, and it goes boom, flying out. Okay, so if we look at these alpha particles, 2 protons, 2 neutrons, are emitted as an alpha particle. So we've got the mass number and the charge right over here. So we've got 4 and charge 2. Beta particles have no mass and a -1 charge. Positrons, no mass and a positive charge. Gamma radiation, no mass and no charge. And then a proton, okay, is emitted. Obviously, with a proton being emitted, it's got a mass of 1 and a charge of 1, +1. And then a neutron would be emitted. It would have a mass of 1 and a 0 charge. Remember, neutron, neutral, no charge. Okay. So give the mass number and charge of each type of radiation. So what do we got for alpha? Mass number 4, charge 2. 2 positive. Positron, 0 mass, positive charge. Beta particles, 0 mass, negative charge. Neutron, mass number 1, no charge. And gamma ray, 0 and 0. No mass, no charge. All right? Something good to jot down in your notes. Ionizing radiation strikes molecules in its path, okay, knocking away the electron in the molecules, forming unstable ions such as H2O+, okay? Well, when we lose an electron, that means it's going to be a positive charge. Causes undesirable reactions in the molecules. The molecules are not happy. So these are things that can damage the cells most sensitive to radiation, rapidly dividing the cells in bone marrow, skin, and reproductive organs, causing cancer. This is how cancer spreads. It basically recodes your own cells, and then the more radiation you have, the more molecular damage or mutation that goes on and causes these things to spread. Okay, so how do we protect from radiation? All right, so perhaps I have a radiation gun, okay? I'm going to fire it at you. Now, if I fire alpha particles at you, really, you can just hold up a piece of paper and deflect every shot I make with that alpha radiation, okay? Don't really have to worry about anything, okay? And even thin clothing, and in some cases, alpha particles can't even penetrate your skin. So we're pretty, cool with alpha particles. Float around, do whatever, not too worried. If we talk about beta particles, okay, we need at least a lab coat, gloves, things like that. So we almost need thicker items, so double layer of clothing. So I got my beta gun and I'm shooting it at you. You hold a piece of paper, that beta is going to keep on coming, and it's probably going to go through your t-shirt, okay? But if you've got an overcoat, thick clothing, thick gloves, I'm shooting my beta gun at you, no big deal. Gamma radiation now. Here's a very tough nuts crack. Many of you guys have had probably, or I'm assuming everybody have had x-rays, at least in their teeth. And then they put this giant lead shield over you, or this lead coat. And what it is actually powdered lead. And inside of that, the reason they do that is they use gamma rays to create x-rays, to illuminate the structures inside your teeth and bones and things like that. And what they're, even though if you remember the dentist x-rays, they're directing it into your mouth, but really they want to shield any gamma rays that may escape or anything else from your internal organs because they know it can damage it. Actually, Thomas Edison was one of the first people to really mess with x-rays and gamma radiation, and he used to do all of his experiments on a particular lab assistant, and the lab assistant ended up having burns and things all over his hands. This scared Thomas Edison enough that he refused to ever be x-rayed. Okay, so if I'm shooting a gamma ray weapon at you, you better be behind some thick concrete or a lead shield or something to bounce those gamma particles. So how do we protect ourselves? Well, we want to limit the amount of time spent near any radioactive source. And so, if I've got to be around uranium-235, which I better not be around uranium-235, and, I'm probably not going to want to spend any time with it. I'm going to want to see it and then go, all right? The other thing is increasing the distance from the source. So again, I'll take my uranium-235. I'm probably not going to lick it and, things like that because I'm very, very close to it, even if it's for a microsecond. The closer you get, the more bombardment you're going to see. So you also want to distance yourself from that source of radiation. So if we look at radiation protection from alpha, beta, and gamma particles, we can look at the different types of penetration. Alpha particles, like, boom, well, you're wearing something, so you're good to go. Beta particles, you probably should be wearing a couple layers of clothing and some other things. Gamma radiation, unless you got that concrete wall up, it is going to hit you, go inside you, go through you, all right, causing damage to your body. So look at alpha particles as far as travel distance in the air, okay? I'm shooting you with my alpha gun. How close do you have to be for me to even hit you, all right, let alone do any damage? 2 to 4 centimeters is my range, okay? So that is approximately a little less than an inch to almost a little over an inch and a half, all right? How much is it going to penetrate into your tissue? 0.05 millimeters, nothing, okay? Shielding, we know what shielding is. Typical source, radium-226. All right, now beta particles. Now, I can get you, look at this. I've got 2 to 300 centimeters to work with. So almost 10 inches, and my beta gun is going to be pretty effective, okay? It does penetrate 45 millimeters, so that is definitely through your skin. But how do I prevent it? Okay, well, heavy clothing, coats, gloves. Carbon-14 is an example of that. Now, gamma rays. Here's where the danger is. I can hit you from 500 meters. Now, I am ex-military, and I know that with my M16, I could hit you from about 500 meters. Well, if I had a gamma gun, I could do the same thing. And it will penetrate into your tissue more than 50 centimeters. That's more than 20 inches. That's thicker than most of you probably are. Not me, but most of you. All right, so what do we shield ourselves with? Lead, the concrete, and technetium-99 is an example of a gamma source. So if we do this, okay, what type of radiation do we protect it from? Heavy clothing, that'd be beta, paper, alpha, lead, gamma, lab coat, beta, thick concrete, gamma, right? Let's see if we're right. Alpha, beta. Oh, I should have said alpha for all, because alpha will protect. I mean, it doesn't go through anything, so yeah. All right, so that's our introduction to radiation, and then we'll carry on and radioactive chemistry, and then we'll start talking about isotopes and all of that good stuff.